11.4 Analysis Model. Isolated System. Angular. The outline of this video is as follows. First, we will introduce the principle of conservation of angular momentum, a fundamental law for isolated systems. We will then see how this principle applies specifically to deformable systems, which are objects that can change their shape and, therefore, their moment of inertia. To make these concepts concrete, we will work through a few examples. We will start with an astronomical case, the formation of a rapidly spinning neutron star. Next, we will analyze a more familiar scenario involving a person moving on a rotating merry-go-round. Finally, we will re-examine elastic collisions to see how conservation of angular momentum provides additional insights. We now introduce a powerful new conservation law that is the rotational analog to the conservation of linear momentum. Just as linear momentum is conserved when the net external force is zero, we find that angular momentum is conserved when the net external torque is zero. This is the principle of conservation of angular momentums. The principle states that the total angular momentum of a system remains constant in both magnitude and direction if the net external torque acting on the system is zero. This situation describes an isolated system from a rotational perspective. This idea comes directly from our previous equation, which defines net external torque as the rate of change of total angular momentum. If the torque is zero, then the angular momentum cannot change over time. For example, a figure skater spinning on the ice is a classic demonstration of this principle, which, with no significant external torque from the ice, their angular momentum is conserved. The key takeaway is that for an isolated system, its initial total angular momentum must equal its final total angular momentum. We will now see how angular momentum conservation explains the behavior of deformable systems. These are systems that can change their shape, which in turn changes how their mass is distributed around the axis of rotation. First, recall that for an isolated system with no net external torque, the total angular momentum must remain constant. Angular momentum, L, is the product of the moment of inertia, I, and the angular speed, omega. If a rotating system changes its shape, like an ice skater pulling in their arms, its moment of inertia, I, changes. For the skater, pulling their arms in decreases their moment of inertia. Since the product I times omega must remain constant, a decrease in the moment of inertia must be accompanied by an increase in the angular speed. This is why the skater spins faster. It is important to note that while angular momentum is conserved here, rotational kinetic energy is not, because the skater does work to pull their arms in. This leads to a very useful expression of the conservation law for deformable systems. The initial moment of inertia times the initial angular speed is equal to the final moment of inertia times the final angular speed. Let us explore how deformable systems, like figure skaters and divers, demonstrate conservation of angular momentum, and importantly, where their change in kinetic energy comes from. A figure skater provides a perfect example. When the skater pulls their arms and legs inward, they are redistributing their mass closer to the axis of rotation. This action decreases their moment of inertia, I. Because there are no significant external torques, their angular momentum, L, must remain constant. Since L equals I times the angular speed omega, a decrease in I forces an increase in omega, and the skater spins much faster. But what happens to the skater's rotational kinetic energy? It is given by the expression L squared divided by the quantity 2 times I. Since L is constant and I has decreased, the kinetic energy must increase. This energy is not created from nothing. The skater's muscles do internal work to pull their limbs inward, converting chemical potential energy stored in their body into additional rotational kinetic energy. So for an isolated deformable system, angular momentum is conserved, but kinetic energy can change due to internal work. This slide consolidates our understanding of an isolated system by presenting the three fundamental conservation laws that can apply. The conditions for isolation, however, are specific to each conserved quantity. First, for energy to be conserved, there must be no energy transfer across the system boundary, meaning the change in the system's energy is zero. Second, for linear momentum to be conserved, the net external force on the system must be zero. Finally, for angular momentum to be conserved, the net external torque on the system must be zero. The key insight is that a system can satisfy one of these conditions, but not another. For instance, if you squeeze a balloon, you do work on it, so it is not isolated in terms of energy. But, because the forces from your hands are balanced, the net external force is zero, meaning the system is isolated in terms of linear momentum. Therefore, to apply a conservation law, you must first verify that the specific condition for that law is met. This question explores the relationship between angular momentum and rotational kinetic energy for a system whose shape changes. The key insight is that while angular momentum can be conserved, rotational kinetic energy is not necessarily conserved in this process. First, let us establish our conserved quantity. While the diver is in the air, the force of gravity acts on her center of mass, producing no net external torque. Therefore, her angular momentum, L, must remain constant. When she pulls her body into a tuck, she moves mass closer to her axis of rotation, which causes her moment of inertia, I, to decrease. Now we can relate these quantities to her rotational kinetic energy, K. A useful expression for kinetic energy is K equals L squared divided by the quantity 2 times I. Since the angular momentum L is constant, and the moment of inertia I decreases, the value of this fraction must increase. The diver's rotational kinetic energy increases. This extra energy comes from the chemical energy in her muscles, as she does work to pull her limbs inward. So the correct answer is that her rotational kinetic energy increases. This slide summarizes the powerful analysis model for an isolated system in rotation. This model applies whenever the net external torque acting on a system is zero, which is a very common situation in physics. The fundamental principle is straightforward. If there is no net external torque on a system, its total angular momentum remains constant. This means the change in the total angular momentum, delta L, is zero. This conservation law becomes particularly useful when a system's moment of inertia changes. If an object changes its shape, its moment of inertia, I, will change. To keep the total angular momentum constant, its angular speed, omega, must also change to compensate. This relationship is expressed by the equation: the initial moment of inertia times the initial angular speed equals the final moment of inertia times the final angular speed. As the examples show, this single principle has incredibly broad applications, from the collapse of stars, to the orbits of planets, and even to quantum mechanics. The key takeaway is that for any system with zero net external torque, the product of its moment of inertia and angular speed is a constant. Now let us work through a fascinating example of angular momentum conservation: the formation of a neutron star. We start with a star that has an initial radius of 1 × 10 to the power of 4 kilometers and a rotation period of 30 days. After collapsing, its final radius is only 10 kilometers. Our goal is to find its new, final period of rotation. We model the star as an isolated system, which means no external torques are acting on it. Therefore, its angular momentum is conserved, and the initial angular momentum must equal the final angular momentum. Set I initial times omega initial equal to I final times omega final. By substituting the formulas for the moment of inertia and for angular speed in terms of the period, we find that many terms, including the mass, cancel out. This simplifies the equation significantly, leaving us with a direct relationship. The final period, T final, equals the initial period, T initial, multiplied by the square of the ratio of the final radius to the initial radius. Plugging in the values, we find the final period is about 3 times 10 to the power of -5 days, which is equivalent to 2.6 seconds. The neutron star's final rotation period is incredibly short, demonstrating how a massive decrease in radius causes a dramatic increase in rotational speed. Let us apply the principle of angular momentum conservation to find the new angular speed of this system. Because there are no external torques, the total angular momentum is conserved. This means the initial angular momentum, which is the quantity I initial times omega initial, must equal the final angular momentum, I final times omega final. The initial moment of inertia of the system, I initial, is the sum of two parts: the inertia of the disc-shaped platform and the inertia of the student. The platform's inertia is 1/2 times its mass m times its radius r squared. We treat the student as a point mass, so her initial inertia is her mass m times r squared. For the final state, the platform's moment of inertia is unchanged, but the student has moved to a smaller final radius, r sub f. Her new contribution to the inertia is m times r sub f squared. Therefore, the total final moment of inertia, I final, decreases. By setting the initial and final angular momentum equal, we can solve for the final angular speed, omega final, as shown in the final equation. The key takeaway is that as the student moves inward, the system's total moment of inertia decreases, causing its angular speed to increase to keep the total angular momentum constant. Let us now consider what happens to the system's kinetic energy. While angular momentum is conserved for this isolated system, we will see that its rotational kinetic energy is not. We can calculate the kinetic energy using the formula 1/2 times the moment of inertia times the angular speed squared. The initial kinetic energy, using the initial values, is 880 joules. After the student moves inward, we use the new, smaller moment of inertia and the new, larger angular speed to find the final kinetic energy is approximately 1800 joules. The final kinetic energy is more than double the initial value. So where did this extra energy come from? The system is isolated, so no external work was done on it. The energy came from an internal transformation. To move toward the center, the student must pull herself inward, doing positive work. This work is done by her muscles, which convert chemical potential energy stored in her body into the additional rotational kinetic energy of the system. Therefore, internal work can change a system's total kinetic energy by converting it from other forms. This example examines an elastic collision between a moving disc and a stationary stick to see how multiple conservation laws work together. An isolated system is one where no net external force or torque acts upon it. In this scenario, we model the disc and stick on frictionless ice as an isolated system, allowing us to simultaneously apply the conservation of linear momentum, angular momentum, and kinetic energy. Linear momentum is conserved because the net external force is zero, while angular momentum is conserved about the stick's center because there is no net external torque. For the angular momentum equation, we define clockwise rotation as negative to match the initial clockwise momentum of the disc striking the top of the stick. Because the collision is elastic, the total kinetic energy also remains constant throughout the interaction. Do not confuse internal forces between the disc and stick with external forces. Only external factors can change the system's total momentum. The takeaway is that complex collisions require satisfying specific conditions for each conservation law used in the analysis. We will now walk through the algebraic strategy to solve for the final translational speed of the stick, denoted as v sub s. Since we have three unknowns, the final speeds of the disc and stick plus the stick's angular speed, we must solve our three conservation equations simultaneously. First, we use the relationship between linear and angular momentum to express the angular speed, omega, in terms of v sub s. Next, we simplify the energy equation by factoring the terms for the disk and dividing by the linear momentum equation. This clever step eliminates several variables, leaving a simpler expression that relates the initial and final speeds. Finally, by substituting the disk's final velocity back into our combined expression, we isolate versus sub s as a function of the initial velocity and the system's mass distribution. Remember that the moment of inertia for the stick depends on its rotation axis, which here is through its center of mass. This derivation shows that the final state of an elastic collision is entirely determined by the initial conditions and the geometry of the objects. After performing the calculations with our given values, we can validate the results by checking the system totals before and after the collision. We find that the stick moves at 1.3 meters per second and rotates clockwise at 2 radians per second, while the disk slows down to 2.3 meters per second. Looking at our validation table, the total linear momentum remains constant at 6 kilogram-meters per second, and the total angular momentum is conserved at -12 kilogram-meters squared per second. While the total kinetic energy remains constant at 9 joules, it is redistributed. The disk loses energy, which is transferred into both the translational and rotational motion of the stick. Do not assume kinetic energy stays in the same form. It can shift between linear and rotational states, even in an elastic collision. The essential result is that all three quantities, momentum, angular momentum, and energy, are perfectly conserved for this isolated system. Let us summarize the powerful principle of conservation of angular momentum. The fundamental idea is that if no net external torque acts on a system, its total angular momentum does not change. This means the initial angular momentum of the system is exactly equal to its final angular momentum. This principle becomes particularly interesting for systems that can change their shape, which we call deformable systems. For these systems, changing the distribution of mass changes the moment of inertia, I. Because the product I times omega must remain constant, a decrease in the moment of inertia must cause an increase in the angular velocity, and vice versa. We have seen how this explains why an ice skater spins faster when they pull their arms in, and it also applies on a cosmic scale, like when a star collapses. Finally, it is important to remember that while a system can conserve energy, linear momentum, and angular momentum simultaneously, the condition for each law is different. The conservation of angular momentum specifically requires that the net external torque on the system is 0. To wrap up, let us consider 2 review questions that test our understanding of angular momentum conservations. The first question describes a student on a frictionless rotating stool who pulls in heavy weights. Think about what happens. Because there are no net external torques on the student stool weight system, its total angular momentum is conserved. Pulling the weights inward decreases the system's moment of inertia. Since angular momentum is constant, this decrease in inertia must cause an increase in angular speed. Finally, the rotational kinetic energy actually increases. This is because the student does work to pull the weights in, converting their own chemical potential energy into the system's kinetic energy. The second question refers back to the disk and stick collision. It asks why angular momentum is conserved even though a force is clearly exerted. The key is that the force between the disk and the stick is an internal force to the system. The stick exerts an equal and opposite force back on the disk. These internal forces create torques that cancel each other out. With no net external torque, the total angular momentum of the system must be conserved.